Today, we're diving into a really cool new way to learn one of the toughest subjects out there, quantum computing. We're going to look at a program that took on the single biggest roadblock in the field by perfectly connecting super deep theory with intense hands-on practice. So, if I ask you that question, what's the first thing that pops into your head? You're probably thinking about the hardware, right? Building stable qubits, fighting off decoherence, and yeah, that's a huge deal. But what if that's only half the story? You see, the real bottleneck, the thing that truly keeps researchers up at night, isn't just building the machine. It's the absolutely massive cost of actually running anything on it. Every single operation on a fault-tolerant quantum computer comes with a price tag, and that price is, well, it's through the roof. And that cost has a name, the T-count. Think of it this way. If your quantum algorithm is a long road trip, the T-count is how much gas you're burning. The goal is to get to your amazing destination using as little fuel as humanly possible. So, in this world, a lower T-count isn't just a good thing, it's everything. So, how in the world do you learn to lower that T-count? Well, this is where the iQuHACK program we're looking at got started, with a masterclass in pure theory, one that was specifically designed to give people the exact mental tools they needed to crack the code. To get a handle on the cost, you first have to know about the two basic kinds of quantum operations. On one side, you have the Clifford gates. They're useful, they're the workhorses, but they're computationally cheap. In fact, your laptop can simulate them, no problem. But then you have the T-gate. This is where the quantum magic happens. It's the source of real quantum advantage. And, you guessed it, it's the main reason that T-count gets so high. Now, the workshop, which was led by Dr. Yudong Cao, did something absolutely brilliant. It didn't just hand out a list of tricks on how to lower the T-count. Instead, it focused on a much deeper question. Why? Why is the T-gate so darn expensive in the first place? And that little shift in perspective, well, that changes everything. And the key to unlocking that why was this idea called phase polynomials. Now, stick with me, this is a pretty advanced algebraic concept, but the workshop brilliantly connected it to something more familiar from the classical world, error-correcting codes. And doing that gave everyone a powerful new lens, a new way to actually see the hidden structure inside these quantum circuits. It's like giving them X-ray vision. All right, so with that deep theoretical foundation firmly in place, it was time to move from the classroom to the arena. It was time for the ultimate quantum challenge. The goal was incredibly direct. We're giving you a series of quantum operations. Your job? Compile them into a circuit with the absolute lowest T-count you can possibly achieve. The theory lecture was over. This was all about pure, raw performance. And what's so smart is how the challenge was put together. It wasn't just a random assortment of problems. It started with some simple calibration tasks to get your feet wet. Then it moved into real-world scientific problems, like simulating an icing model. And it ended right at the cutting edge, with problems from the frontiers of current research. A perfect escalating difficulty curve. And because of that brilliant design, you couldn't just brute force your way through it. The problems were all connected. The teams that won weren't the ones who treated each task as a one-off. No, the winners were the ones who developed a single, powerful, and general strategy, a true compilation pipeline that understood the underlying structure of it all. And this is where it all just clicks into place. This is the big aha moment, when everyone realized that the abstract theory they had just been wrestling with, it wasn't academic at all. It was the secret weapon for winning the entire competition. To put it plainly, the workshop wasn't just related to the challenge, it was a perfect blueprint for it. Every single concept from that theory session was directly applicable, giving these teams the exact mental models they needed to tear these problems apart. Just look at this table. It shows the connection perfectly. The theory of Clifford plus T universality, that was the entire foundation of the challenge. Those abstract phase polynomials, they turned out to be the key to cracking the hardest tasks. The T-count itself, that became the scoring metric. It was a perfect one-to-one match. And get this, it gets even better. The challenge recommended a specific software tool to help out, a compiler. But because of the workshop, participants didn't just see this tool as some magical black box. They actually understood the deep mathematical logic, those Reed-Muller codes that made the tool work in the first place. They could think with the tool, not just blindly use it. So what's the big lesson here? I mean, this is more than just a story about one great event. This whole structure represents a powerful new model for how to teach any deeply complex technical field. By seamlessly weaving the why into the how, the program went way beyond just basic instruction. It delivered something much, much closer to real, professional-grade training in the art and science of quantum software engineering. And this quote just sums it all up perfectly. Good training teaches you how to use a tool. Great training teaches you the math and the logic behind the tool so that you can push its boundaries, improve it, and maybe one day build something even better. That's the difference between a user and an innovator. And that leaves us with a final thought to chew on. This theory-first, practice-focused model was incredibly effective for quantum computing. So you have to wonder, what other complex fields, from AI development to biotechnology, could be supercharged by this same powerful approach?